Good morning. We are going to work on the Unit 2 Review B today. So if you stay and watch, you should have all the answers and be successful on that, turning that in. And also, I'm first going to go over the 2.7 worksheet because I just want to make sure that everybody is supported to gain understanding before the midterm. And if you want to meet with me at all to go over your worksheets, you can send me an email or a remind text. I'm happy to schedule time to go over your worksheets for Unit 2 and see what questions you have. So let's go ahead. I'm going to share my screen here. And also, I think I have the worksheet open. Okay. So 2.7, question number 1. I'm going to kind of go through this quickly here. It says, this is the U.S. historical debt. We've got 2 things we have to fill in the table here. Oh. Okay, so the 2 columns we have to fill in are the T's and the debt in billions. So T's, it says, let T be the year since 1950. And 1950 happens to be our first year. So 1950 minus 1950 is 0. 1951 minus 1950, the base year, is 1. And so on and so forth is going to be 34. 48, 62, and 68. And then when we're filling in the debt in billions, remember the first period here is hundreds, then it's thousands, then it's millions, and then it's billions. So the first 9 place values you don't need. We're going to round to the nearest one. So this one would round down. So 257. And then it went down to, just a little to 255. Then it went up to 326. And then notice we're still canceling out the first 9. So now it feels weird to write this, but there's 1,572 billion. 5,526 and 16,066 and 21,516. So part C says find a regression equation. So we've been calling it this, the best fit model. So whenever it says regression equation, it really means the best fit model. So I want you to test the linear and the exponential. And my people on live, who can tell me how do we choose which is best?
From the correlation coefficient.
Okay, and what about it? What am I looking for?
You're looking for the R, which is you want it to be the closest to 1.
Okay. And if there is a negative relationship, which we're going to see on the next page, so I don't want to give it away. So on this one, we're looking for the R that is closest to 1. And sometimes you have to think about life in context. So some of you on the 2.6 worksheet, you chose linear model and some of you chose exponential, and that's okay. The exponential had the highest R, but I could see where in real life, I would probably choose the linear. So as long as you interpreted everything okay, you were good. Okay, so I'm going to go to my Desmos because I already have this here. And I will put my Desmos link. And if I forget to, somebody remind me, I'm going to put my Desmos link in JetNet when I copy over this recording. Okay. So can everybody see there's my data. And then I've already typed in my 2 models. Well, let's see, this is my second piece of data. So let's go here, and then I'm going to insert an expression. So there's my exponential model, and I'm going to do, my data set up here was called Y2. So I have to use Y2 tilde mx2 plus b. Okay, so here are my two models. I'm going to turn off the colors of my other ones down here because I don't want to use those right now. So the data that I have on my screen is the linear model green for this data here, the debt in billions, and then the black is the exponential model. And so we're going to use the R from both to make a decision on which one's better. And who can tell me which one is better in this case?
The exponential model is.
Okay. The R is 0.9861. It is definitely better. So we are going to, the R is only going to be used for the correlation coefficient to tell us which one we're choosing. The parameters, the values underneath the word parameters, are the two values that are going to go into your equation that you're going to write, your recipe that you're writing for me to let me know which equation you're using. Okay, so we're going to use 188.381, and then we're going to use 1.07 as our growth factor. So let's go back to my paper. There's just some, I think, some misconceptions that I want to clear up today when we go over this. So exponential, because R equals 0.9861 is closest to 1. So my model is this. And I'm going to put 188.38 times 1.07 to the x. This is when I ask for the model, I want you to give me this once you've gone to Desmos. Also, a suggestion for your midterm is doing your work in Desmos and just having one file, and you name it midterm with your name in there. And then all your work is there, and just keep hitting save throughout, hitting save. And then you can upload that with your midterm. And that way I can see your work. So if you do like a percent error or a percent increase or decrease problem in Desmos, I can kind of see how you typed it in to point you in the right direction if you went wrong somewhere. So it says, identify the parameters of your equation, explain both in context. Okay, so A is 188.38 and B is 1.07. Okay. This is our Y-intercept. Y-intercept. When it's an exponential equation, A is our Y-intercept. So that means I'm going to describe 0. Well, 0 is my first year, 1950. So the model predicts that in 1950, so I'm acknowledging the 0 year, the U.S. had a national debt of 188.38 billion. Now, I want to acknowledge that is not the actual data point. The actual data point that is real, true in life was 257. So we can already see that our model underpredicted a little bit, right? By like 70 billion. But that is what the interpretation of the Y-intercept is for our model. Then this 1.07 tells me this is my growth factor. So when I ask for growth factor, I want you to give me this. This is the multiplier. But the percent change is found by taking B and subtracting 1. So 1.07 minus 1 is 0.07, right? And so that 0.07 says that the U.S. national debt is increasing by 7% each year. Okay, so even though the years up here are not increasing 1, you can't find this growth, percentage growth by hand because they're not increasing by 1. So it's not accurate. So that's why you need the model from Desmos. And you're going to write, this is what it means to interpret in context of the situation right here. Okay. Then it says, predict the total US debt outstanding in 2025. So I need to know what year that is, right? Because I'm not going to look up 2025 because I'm using this base year of 1950. So 2025 minus 1950. If you're not sure, type it in your calculator to get T equals 75. So there are a number of things we can do. We can, which is the same as X, right? In our, in Desmos. So let's go to Desmos and check out what we can do to find that. So I'm going to go here and just insert another line so it's right with this. So I can say X equal to 75. And it's going to go up here at 75 and it's going to put a gray dot. And because I'm using this exponential one, I can turn off my green line if I want. So I'm only seeing the intersection of 75 and my exponential model, which if you hover over the gray dot where my mouse is, you'll see that X does in fact equal 75. And it looks like the debt is approximated to be $33,048 billion, which is really 33 trillion. Okay, that's one way. I'm going to turn this back on just so it's there. So another way is you could use the slider. So you could go on the as long as you're using the exponential model, you could slide to where it equals 25 or 75, and you could do some estimating that way. You could also simply type in the model that we have and put 75 as X. So there's a couple of different options there. Any questions from my live folks? Okay, so we're going to look at the second problem for worksheet 2.7. And similar in fact that they gave us some data. It says the number of architects employed in Indiana since 2007 is listed below. So first off, we have to fill in our X years. They didn't tell us to do that, but we need that information for Desmos. So 2007 is our base year, so it's 0. And then it goes to 2009, subtracting 2007 is 2. And it looks like it goes 0, 2, 4, and 6. Okay, and this one's nice because it did explicitly say, find both a linear and exponential model. I want you to write both of those here and here. And we're going to just write the R while we're at it. And anybody on the live call want to tell me what looks a little bit different about this data set than the last one we did?
This one's decreasing.
Okay, so this one is decreasing. So as X increases, Y decreases. Okay, so let's go ahead and turn to Desmos for a minute. We'll get all of my data's already in there. And I'm going to turn off the last data that we used for just a moment. And I'm going to turn on this data. Okay, so, Okay, this is a little bit more appropriate to see. Can everybody see that okay? So here is my model, a linear model that I did. Here's my log mode, my exponential. Make sure if you copy your model for exponential, make sure you click on the log mode box because it doesn't automatically save the clicking on the box. And you won't have an R if you don't click on the box. So there are the parameters for the linear M and B. We're going to write those down on our paper, and then A and B for the exponential and the R's. And so the R's, last time Stephen said that we were trying to get an R that was closest to 1. But what's different about the R's this time?
They're negative.
Okay, so they're negative. So are we still trying to get to a positive 1, the one that's closest to a positive 1?
No, it'd be -1.
Okay, so when we have a decaying model, we're trying to get the R that's the closest to a -1. So let's go ahead and show my paper so that everybody can see how I would write these out for my 2 models so I can decide which one I'm going to do. All of this should be guiding you or helping you, or else double checking what if you've already done your project, what you would be doing on your project here. So my linear is a -90x plus 1445. And there's my R that goes with the linear. And then my exponential is 1454.85 times 0.927. I rounded it to, you could have used 2 decimal places, it's fine, to the X. And there is the R for the correlation coefficient for the exponential. Now, the one that's closest to a -1 is which one? Anybody want to tell me?
The exponential.
So the exponential is the better fit. Now, besides the fact that it has the best correlation coefficient, we might want to just kind of look at the graph and think about the situation, because this is always important as a statistician or somebody working with data in any industry. It's important to think about the context, right? The story of what's going on. So let's go back and look at the data for a minute. So if we choose exponential, which that is our best fit, it looks like we're going to decrease, quite quickly, and then it slows down and then decrease. And this is the number of architects. So, I mean, we're always going to be building buildings, right? So do we think that we're ever going to just not have any architects designing buildings, even if they're using CAD and they're using, I mean, we can't have, I guess we maybe could make a robot smart enough to design all these, but more than likely we're going to have humans called architects designing buildings. If we do the linear line says that after about year 16 or so, let me get here. So, yep, just about year 16. So the year 2023, so next year or 2 years, we're not going to have any architects. So that's also something to think about, is just the realistic story of what's going on. So I think even though our R is also the best for exponential, I would also say exponential is probably the best in the decay, because exponential, you'll notice we could get really, really close right here, and there's still at least 1.7 architects, and that's in 88 years. So an exponential never actually arrives at 0. So exponential would never actually say you would ever have 0 architects. Okay, so that's just my 2 cents there. So let's look at letter C. It says, use your model to predict the number of architects in 2012. So 2012 is subtracting 2007 is year 5. And a number of ways we could do that in Desmos. I'm going to just go back and share my Desmos quickly here. And I could go to X, no, X equals 5. And it's going to give me a gray line at 5 right here. And they both, it looks like, equals about that. But about at year 5, which would be 2012, there was about predicting about 995 architects. And then letter D says, use Desmos calculator to predict when the number of architects will be 500. Draw a rough sketch of the graph. So then we can go down here and say Y equals 500. And again, it's going to give us a gray dot. We are not using linear, so I'm going to just blot out my linear for now. We're only looking for this intersection right here on the exponential. So it's about year 14. So approximately, X is approximately 14 years. Let's go back to my paper here. And you can see that letter C, in 2012, there were approximately 995 architects. Here's approximately year 14. There will be 500 architects. And that's in Indiana, right? We should probably acknowledge that, but it's not here on Earth. It's not in the US. It's in the state of Indiana. That's what they're predicting. Any questions from my live folks?
Nope.
Okay, I noticed something that was not on the worksheet 2.7 that I really think is important to go over. On the second problem, when we were looking at the number of architects, I don't ask you to describe the parameters. And this is an important one to know how to describe because it's decay, right? It's going down. I want to make sure everybody knows how to describe that in context. So you're going to take that percent, you're going to find the percent change, which is a decrease for us, right? By taking your growth factor, the 0.927, and subtracting 1. And it feels like you should say 1 minus, but it's always the growth factor subtracting 1. And that's going to come out to be a negative, which solidifies the fact that it is a decay, it's decreasing. And that comes out to be negative 0.073, which means that the number of architects is decreasing by 7.3% each year. So I wanted to make sure everybody had an experience to explain that. So let's go ahead and get out Unit 2 Review B and spend some time going through this. So it says, the first one, you're comparing Walmart 2 bags of 15 ounce of these Dorito chips for $7.65, but Costco offers a 64 pack of the little mini bags for $32.99. So the first one is asking you to calculate ounces per dollar. Now, we're all different on how we would look at this problem. And so usually I would say just calculate either way. Some people would calculate the ounces per dollar. But my natural thing would be to look at the cost dollars per ounce for me. And so there's 2 ways you could look at this. So I'm going to just put up the 2 ways for the Walmart here. So you could look at dollars per ounce and then getting a unit rate. So the 2 packs make 30 ounces. And so this becomes 26 cents per ounce. And if you did the ounces per dollar, you're getting 3.92 ounces per dollar. Any questions on that one? And then I followed that thinking down for the second one with the Costco version. And to get that, you had to take 64 and multiply by 1.75 to find out how many total ounces you're getting, right? So 64 times 1.75 means that you actually have, this is 32.99 divided by 112 ounces. And then the the Costco is 29 cents an ounce, and the other way to look at it is 3.39 ounces per.
You heard.
How do you decide which one's better?
I'm doing homework. Anybody that's live have an idea? How do we decide which one's a better deal?
The Walmart one looks better because you're getting more ounces per dollar.
Okay. So if you're going to use this version on the right, you're looking for a larger number because you want more product for the same money, right? If you're using this method on the left, you want a smaller number, the 26 cents instead of the 29, because you want a smaller price for the same amount of product. So two different ways to think about it, but you should always arrive at the same choice, and Walmart would be your best. Any questions on problem number one? Okay, let's turn to problem number two. So it says calculate a unit rate in terms of meters per second. So they want length versus time. So 100 meters for the 9.58 seconds. But they asked us for a unit rate. So that means we want to get it per one. And when we do that, we get a rounded 10.44 meters per 1 second. Then letter B says, use his speed, Usain Bolt, and you can use either. You could use the original that they gave us, or you could use the unit rate. But we want to put that into miles per hour. So I want miles per 1 hour as a unit rate over here. That's my goal, right? This is what I want and what I'm starting with. So I'm going to start with the 10.44. 10.44 meters per 1 second. And so I'm going to have to use some unit exchange to exchange my meters into miles and my seconds into hours. Has everybody live had a chance to look at this, or do you want just a minute to? So because I'm starting with meters, I'm going to use this exchange here. That 1 meter is the same as 3.28 feet. So my meters cancel. Then I'm going to multiply. I need to get rid of feet and then miles. So I'm going to use the one that kind of wrapped around here. So 1 mile is 5,280 feet. So that means my feet have to go on bottom because I need to cancel out that unit. It's the same as 1 mile. And I'm going to circle miles because that is a unit I want in the end. So canceling out the others and then circling miles. Now I have to get my seconds into hours. So I know there are 60 seconds in 1 minute, and I have to put my 60 seconds on top because to cancel out with my seconds are in bottom in the exchange that I was given. And then I have to exchange 60 minutes for 1 hour. And then my minutes are canceled and I'm going to circle hours. So in the end, what I want over here should be what I've circled over on the left. And it is. I circled miles and I circled hours. And now we should multiply straight across on top and bottom. And when you do that, and you get this right here. And then your final dividing to get the unit rate comes out to be, he is running at about 23.35 miles per hour. He is fast. Crazy. Then it says calculate a unit rate. Okay, so we want per one, minutes per mile. Excuse me, minutes per mile. So I'm already in miles up here, but in hours. So I'm going to use this, what we were given here, because it already has one of the units I want miles in it. But remember, they're asking us for time over distance. So I have to flip these around. So 1 hour, he travels 23.35 miles. Because what I want over here is minutes per mile. Okay, so my miles, I don't have to do any exchange with, but my hours to minutes I do. And so I have to multiply by 60 minutes over 1 hour. So my hours cancel. I have minutes and I have miles. So it becomes 60 over 23.35. And when I divide to get my unit rate, I get approximately 2.57 minutes per mile, which is crazy fast. And then letter D, it says, what is your answer from C mean? Well, he's saying can run 1 mile in 2.57 minutes. So just over 2.5 minutes, he runs a mile. I had a friend in high school who broke our high school record at just over a 4-minute mile, which I thought was crazy because when Mrs. Main runs, if I'm all out, you know, giving my best in just 1 mile, I'm maybe an 8-minuter, and that was a long time ago. So, yeah, 2.5 minutes is crazy. Okay, question number 3. I'm not going to spend a lot of time on because it's really just getting you to make a scatter plot, which we're going to do a bazillion of those today. The one thing I do want to make sure everybody knows how to do is to find their years in X, because that sometimes is a struggle. So it's saying that they want the number X to be the number of years since the 2008-2009 season, which is our first year. So that's going to be our 0 year. And then it looks like they go in ones, which is nice. So that ends up being 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I'm not going to waste any of our time making the scatter plot because we're going to do that here in just a minute. So let's look at question number 4. It says the U.S. Army is offering a one-time bonus of $16,000 for shipping to boot camp in 30 days and a yearly wage of $25,558 for a specialist with less than 2 years of experience. Write a linear equation. So I'm already telling you that I want it to be this form. modeling your total income, assuming you will ship in 30 days. So the 30 days is a bonus. It's a one-time constant amount. So that is our Y-intercept, right? As long as they do that, they get the 16,000. And I put plus because it's a positive. And then every year, so the total amount that they're going to earn, right, is going to be based on the number of years, because it says the yearly wage is going to be this 25,558. So 25,558 times the number of years that they work. Then it says, how long will it take to earn 35,000? So 35,000. Oh, yeah, now we're here. So 35,558. We can put this into Desmos. So I'm going to share my Desmos screen with y'all. And you can see, I'm going to type in my equation. So y equals 2558x plus 16. Oh, what's that? I missed a 5, didn't I? Okay. Excuse me. Now mine is looking like a straight line. It's not very good scaling. So I'm going to click on my equation that I just typed in, and I'm going to go up to the gear where it says edit list right here where I'm pointing. And I'm going to click on that. And then it gives me the option to make a table. And yes, ma'am, I do want the table because the table is going to help us, but also it's going to allow me to click on my zoom fit with my magnifying glass. And then you can see that my scaling is much better. And then up above it, I already typed y equals 345,000 because I want to know where it crosses that. And right now I can't see where it crosses on my screen because of the scaling. So I'm going to have to just keep moving over or else move out. Zoom out. Wait, zoom in. Oh, I know. I turned off my line. There we go. So, and we can go ahead and click on that. So we can go over here and see that it's at about 12.79 years, depending on where. Yeah, 12.8 or so, 12.8 years. So 12.8 years to do that. Okay, the next question is, I'm just seeing if I've got it here in Desmos. No, so that's all right. Okay, so let's go back to my paper here. We're going to talk about these Tasmanian devils. Question number 5 says the population of the Tasmanian devil can be modeled by this linear equation here. They gave us the R, correlation coefficient. And these are years after 1996. It looks like they're decreasing, right? Because our slope is negative. And it says identify the slope and Y-intercept, and identify the slope and interpret in context. So the slope is a negative 12,610. And it's per year, right? Because we need to make sure that we know our units. So this is devils, right? The animals per year. So we are going to say the population of the devil, you want to write Tasmanian, it's fine, decreases by 12,610 each year. So make sure you're referencing the years or whatever your denominator changes, and then also the units in the numerator. And then B says, identify the Y-intercept and interpret that in context of the situation. So the Y-intercept is a particular point, and it's when X equals 0, and it's this value right here. So the 256,412. So in your sentence, I want you to describe what the 0 means. And so the 0 means the first year, which is 1996. So we can say, we predict that in 1996 there were, and because we're using a model to predict, we don't have the exact value, we're going to say approximate. So we predict that in 1996 there were approximately, so you can just write approx with a dot, 256,412 Tasmanian devils, period. Devils. Wow. And then C says, is the equation a good model for the population? And I want to explain. Anybody want to chime in? What are your thoughts? So I'm going to say, yes, it's a good fit because R is equal to negative 0.966, which is very close to 1. So when we ask, you might be thinking, I've mentioned it before, but you might be thinking, I don't even know what would be a good number for R. So a statistician usually says anything that's 0.8 or bigger is reasonable. 0.5, horrible, not good at all. So on the one where we were trying to predict your grade on the exam using your percent attendance, remember, I think it was like the 2.4 worksheet, that R was 0.49. It was horrible. I wanted you to say it was a terrible model, not a good fit, can't use it. A lot of you weren't quite there yet in your understanding, and that's okay. So I didn't count that wrong, but I want to make sure that you're looking at that R. Any question from my live folks? Okay, so let's move on to question 6. We're going to head to Desmos. So we won the Michigan Mega Million lottery ticket, which would be awesome. We only won $2, $200 though. You have to match 3 white balls and a mega ball to get the 200. So let's say you put it into a savings account, and after 6 years, you had $260.02. So I want you to find the growth factor and the growth rate, but you're going to do that in Desmos. Okay. Now this one is perfectly the same. So you could do this one by hand, but it's good to know how to do this in Desmos. So let's just go there. And you can see I already have my data. And once you type in your data and hit the magnifying glass, then this is probably what your scaling will look like. Looks very linear, but they're asking for a growth factor. So we're going to assume it's exponential. So if you scroll down, you can see that I did put in an exponential model with the log mode, and it came out perfectly, R equal to 1. So we know it's a perfect match. And my A is at 200 and my B is 1.05. So my growth factor is 1.05. So let's go back to the paper. And that is 1.05, but the growth rate, right, is taking, that's my percent change, is equal to B minus 1. So 1.05, oops, minus 1 is equal to 0.05. And then B says, interpret that growth rate. Okay. So when I ask you to interpret the growth factor, I always want you to turn it into a growth rate, the percent change, and give it to me in context. So this says the amount in my account is increasing by 5% each year. Increasing because it's positive when I subtracted 1, and I turn that into a percent. So move my decimal to the right to the amount in my account is increasing by 5% each year. Now, C says, write an equation to model the situation. So we are going to say Y equals A in Desmos was 200. And my multiplier, my growth factor was 1.05 to the X. A and B, my parameters. I've been using that word a lot, parameters. And it says, what will your account be worth in 70 years? So, anybody live want to help me with this?
I got $6,085.28.
Okay, let's check it out. So I could just put 70 right in there and type that into Desmos, right? Lots of things you can do here, and Desmos is so efficient. So in Desmos, let's see if we match what he did. So Stephen did just that, and you can see in Desmos, I put that in, and is that what you had, 6,085 and 29?
Yeah.
6,085 and 29. And the cool thing is, that's one way you could do it. You could also say, if you just type in the equation we came up with, so Y equals 200 parentheses 1.05 parentheses, no, to the X. And then if you go up to the gear and make that a table, then down in your table, you could just put 70 and it will come out as well. That only works if you have the equation. If you just have data, it doesn't work. It only works when you have the equation or the model from Desmos. Okay, then E says, when will the account be worth $20,000? So you can see right here, I typed Y equals 20,000. I'm going to turn that on. I turned my graph off just for the purpose of looking at other things. So I need to, my scaling is not at 20,000, right? I'm at 200 right now. So I'm going to zoom out for a minute so we can see when it gets to 20,000, and it's way down the road here. There it is. So far down the road, it's making some shading issues. Oh, I've got other data that's showing up. Oh, my raw data. So I'm going to click back on where it says Y equals 20,000 so that it will take me to the right spot up here. So it looks like in about, I'm not quite on it right for my, here, so about anywhere between 87 and 94 years. It says 87 right there, but that's just my line. It's going to stay there. So I'm trying to hit this. So yeah. So anywhere between 87 and 94 years. And how you estimated that there. Any questions from the live folks again? Okay. So let's go back to the paper here. This is how I wrote mine out. I'm going to move on to question number 7. I'm giving you an equation. This is talking about caffeine in your blood after drinking coffee. So we've looked at one of these coffee ones before. And it says decay factor. Well, we keep calling it a growth factor. So we're just calling it a decay factor here because that multiplier is less than 1. That's the only difference. So that's 0.89. And it says interpret it in context of a situation. So I need to find my percent change by taking B and subtracting 1. And I get a negative 0.11. And that is a negative 11%. So I'm saying the amount of caffeine in your system is, I'm using the word decreasing because it's negative, decreasing by 11% each year. Letter B says, what is the Y-intercept? Interpret it in context of the situation. So the Y-intercept is 0 and 280. And to interpret that means 0 is when I started measuring, right? When I, maybe at the max, right? When I finished my coffee, I was probably at the max. When I finished my coffee, I had 280 milligrams of caffeine in my blood. It only went down after that, unless you keep drinking coffee, of course. So it says, how much caffeine remains after 6 years? 6 hours. Obviously, I need more caffeine. So after 6 hours, so hours is my X, right? So I want to know when X equals 6. So I'm going to go to Desmos here for a minute. And I've typed in my equation, just so y'all know. I've typed in my equation and I already went to the gear. Jeez, I'm so sorry. Some mornings are better than others. So I already went to my gear and created my table, and I typed in, that was a mistake, 6 hours. And I got 139.15 milligrams. Now, D is tricky. That's where I had the other number in there. It says, when will 5 milligrams of caffeine remain in your system? So this is this is forever here. So I'm going to adjust my scaling on my graph for just a minute, and I'm going to take out this other data set. And I think I have other data sets I need to yep, I'm going to hide. Okay, here's our data set. So I want to find when it's at 5, which is like way down here where my mouse is, which is almost hard. So we just did some estimating. So I said, I'm guessing in 20 hours. So when I put in 20 for X, I got 27. So I know it's longer than that. So I'm going to guess 30 hours. Oh, I'm down to 8.5 milligrams. So I'm going to guess 32 hours. I'm at 6.7. I'm going to guess 33 hours. I'm getting close, 5.98. So 33, maybe 0.5. Close. 33.55. Oh, 33.56. So I'm going to say 33.8. 34. Oh, 34 is closer. 34.5. It's pretty close. 34.52. Oh, 34.532. I'm getting closer just by adding decimals, right? I'm getting closer and closer and closer. So about 34.5 hours. So it takes that long for the caffeine to be completely out. So you'd have to go without caffeine for over a day, almost 2 days, before you'd be like, oh, I don't have any caffeine in my system. That's probably why, like, every 24 hours, you're kind of a headache if you don't have that caffeine that you're used to having from coffee, because it's like, oh, wait, I'm going through a little bit of withdrawal. So if you give me some, I'll make you happy again. So, right. So you give your brain some, and then your brain's like, oh, I feel better. Okay. Enough of me talking about that. Okay. So we're on question number 8. Just 2 more to go. Number 8 is looking at our Fibo scores, which is our your credit, right? Your credit score, to make sure that you have shown businesses that you are able to borrow money and pay it back without being late on your payments and all that good stuff. So it says your FICO score helps you get a lower interest rate. Usually when you have a really high good credit, you get a lower interest rate when you borrow money for houses and cars and such. So it says, find an equation of best fit, which means I want you to find a linear model and an exponential model in Desmos, and then choose which one is better based on the R. So let's go to Desmos and put in our data, which I did. So here is my data. I've got my mouse around there right now. And then I've already typed in my model. Make sure that you click on your log mode box, and your model should look about like this. And our data looks kind of funky. I don't think it looks like either. It's perfect. But we're going to look at our R. They're both a negative. So we're looking for the one that is most closer to -1, which would be the linear in this case. Right. And it's so, okay. So that's the one I'm choosing for this one, is a linear, this one right up here. I'm going to turn off my exponential so we can just see that. So the linear here is, my slope is a -0.068. My y-intercept is 53 even, about, well, 0.0026. It does say use 4 2 decimal places. And then our correlation coefficient is a -0.9522. So let's just go right then on our paper. So we're choosing linear. So we have a -0.07. It said 2 decimal places, x plus 53, and state the correlation coefficient, which we use the linear, which is a -0.9522. What does it tell you about this equation? So very close to 1. linear is a good fit for the data. Okay. Use your equation to predict the APR of an individual with a 300 FICO credit score, which is pretty low, pretty low, pretty low. So I'm going to go to Desmos here and put in through, we want to find out a 300, right? Up here. So I'm going to go to my linear model and I'm going to go down. I'm going to go when X equals 300. It's going to be real high. Right? I can't quite get it there. I'm really close. I'm very, very close. I just can't get quite close enough. Okay. So it's about a 32.5%. Really high interest rate. That's crazy. Letter D says the minimum possible FICO credit score is 300, and banks typically require at least a 500 score to be approved for a loan. Why might your prediction from C not be accurate? Because C is kind of outside the realm of our data. Because 500, we don't have any data. So let me go back to my paper. So this, hopefully you can see my paper right now. You can see my paper. So because our data is between 500 and 720, we really should not be doing predicting outside of that. Okay. So it's outside of the scope. 300 is outside of the scope of our data. So there's been other times and other worksheets we've been outside of the scope of our data. I just haven't really talked about it. But whenever you do predicting, you should really always be doing predicting within the data scope that you already have. So predicting lower than 500 is not good. And predicting more than 720 is not good, because you're saying, I'm going to predict what's going to happen way down here, or up here, which isn't always great to do.
How did you get 32.5%? Did you plug in the 300 for Y or for X?
For X, because X is our FICO score.
Okay.
Yeah. X equal to 300. I just use the scroll bar on my the slider on the equation, but you can also go to Desmos. We could have said X equal to 300. Oops, here. And then just clicked on the intersection there and it says 32.55, so 32.6.
Okay.
Yeah, that's another way. Great question, great question. Okay. Is everybody ready to move to the last question, question number 9? So it says the national U.S. historical debt outstanding is shown in the table. So complete the table here. So we have to fill in our T's. And it says use T's since 1954. So the first year is our 0 year. And then it looks like it increased by 1. And then 1965 subtracting 1954 is 11. And Then we get 1973 minus 1974 is 19. And then 24, 43, and 40, oops, 63 is the last one. Sorry about that. It says complete the table. We did. You make a scatter plot. We will. And the R to determine which model is the best. Then write the model and round each parameter. Okay, to 2 decimal places. So I'm turning off the things we just did in Desmos. And I'm going to turn on the data we have here. So I'm going to hit my magnifying glass so we can see it. There's our data here for the debt outstanding, U.S. national debt outstanding. And then I'm going to click on, there's my 2 models that I came up with. And make sure your login box is there. Yes, it is. And we have to decide which one is the better of the 2 fits. And which one would we fit there?
I chose the exponential.
I did too. And that R is 0.979. That's what I go to first. And I just look at that first and kind of go by that. So 0.979 is definitely much better R than the linear is only 0.88. So I'm going to write out my model here. I'm going to share my paper again so everybody can see my model. The model that I'm going to use is um, 187, right? 187.42 times 1.07 to the x. Plus 0.97. Okay. Then it says, use the model to predict debt outstanding in 2018. So to do that, it's going to be T, right, or X. T is equal to 64 years. So back to my Desmos link. And my Desmos length, I put X equal to 64 there so I could have it draw a line. And there it is. And it gave me and I'm using the curve, the black curve, not the purple line. And it looks like it's about 19,072 billion. So 19,072.3 billion. Which is really 19 trillion. So you could say, or 19 trillion, which is crazy. What is R and what does it tell you about this model? So R is 0.979. It is a good fit for the data. And then D, the actual number debt outstanding in 2018 was 21,516 billion. So we're going to be comparing to this billion. Calculate the relative error between your answer from B, right here, and the actual. So remember, when you do error, it should be the predicted. subtracting the actual over the actual. And this is where it is important on your midterm that you're writing out the formula and then filling in your numbers so that I know what you were intending to do. So the predicted is the 19,072.3, and you don't have to put any zeros on there because as long as your units are both in billions, so that's why I'm using this one because it's in billion. And then minus 21,516 divided by 21,516. And I'm going to show you how I type this in Desmos. And there, right here is my where I typed it in Desmos. And I got a negative 0.11, which is 11% under predicted, right? We spent more than what we even predicted, which is a crazy amount. Not good. And it's getting worse. You know, there's a debt clock that you can look up online, and it changes. This is our work right here. Debt clock. My husband follows it, and I'm like, how depressing. No, let's not do that. Let's go look at it real quick while we're wrapping this up. U.S. debt clock. U.S. debt clock in real time. Right here. Isn't that crazy?
Yeah, that's weird.
Mm-hmm. You can look at the population, how it's changing all the time. Largest budget items. Yeah, it's just crazy, isn't it? It's just like, it's cool, all the stuff that they have on here. That is the end for the Unit 2 video. See you for the midterm.